A double today. We have quite a bit to do, okay? So get your notes out, take a look up here, and let's talk about where we left off yesterday. We were doing some calculations, and I want to kind of go over a little bit with you where we left off. We were doing some calculations with electrons and what they do when they change energy levels. We were able to predict, using an equation, delta E equals hc over lambda, we were able to do those calculations yesterday. There was a part to those calculations we didn't have time to get to. I'm going to do that today. Turns out, if you remember from Bill Nye, hopefully you do, again, I would probably have done it in a different order had I not been, if I had been here on Friday. But you may remember Bill and I talked about a couple of things. He talked about wavelength, all right? So like wavelength, we said yesterday, is just a distance between two parts of a line, right? Okay, that makes sense. He also talked about something else, though. What was another word he used? It has to do with waves, besides wavelength. Do you remember?
The energy they put off.
Well, no, he didn't talk about energy. Well, actually, he did a little bit. We talked more about energy yesterday. He did a little bit, you're right. But no, the other one that's related to wavelength and its speed of the wave begins with an F. Frequency. Remember frequency? And the way he remembered that, the way he was talking about that, if you remember, he had a kid on a stick. Remember this? A kid on a stick? And what he did is he turned this little thing, and the waves went by. And the kid counted, 1, 2, 3, how many waves there were going by per whatever, per second, per minute, whatever. That's what frequency is. How many are going by, all right, per some amount of time, usually per second. Now, the thing is, if the waves are all traveling at the same speed, think about this now. I want to use a little common sense. If this wave is traveling at the same speed as this wave, okay, and I got my kid on the stick, what's going to happen to the frequency of this one compared to that one? Yeah, going to be a lot higher frequency for this guy. If they're both traveling at the same speed, he's going to see a lot more waves, right, per second. That's how they're related. Okay, the shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. That's given the same speed. All right, so that's an equation we can actually use to calculate. All right. Oh, I don't want that. That's an equation we can actually use to do some calculations with energy as well and electrons. C equals lambda times F. Now that basically means the speed of light, or the speed of this radiation, these waves, equals the wavelength times the frequency. Now, I'm just going to do one example with this one, but there's a lot of possibilities here, okay, of how I can ask the questions. We already got yesterday, don't copy this down. We got this equation yesterday. Delta E equals hc over lambda. Today, we got this equation. C equals frequency times wavelength, wavelength times frequency. You can see wavelengths in both of these, and so is C. All right? And we can actually interrelate these. So I can be asking you for multiple things here. I'm never going to ask you to calculate for H. Why not? Why am I not going to ask you to calculate H?
Because it's always the same.
It's a constant. Yeah, it's always the same. I'm never going to ask you for C. He's a constant. He's always the same. But I can ask you for wavelength, energy, or frequency. And depending on what you're given, you may have to use one or both of these equations. And we'll talk about that possibility. But I'm only going to do one example right now today. I'm going to give you the worksheet that the other class got yesterday. I'm going to give you some time to work on it. But we are not going to have that full period because we need the time, the second half of this period, to work on some other stuff for the lab tomorrow. All right, so let's do this first example using this equation. We already did two examples using the harder equation. This was a pretty easy equation. Find the frequency of electromagnetic radiation of a wavelength. It has a wavelength of 5.59 times 10 to the negative 5th centimeters. Now I threw another little curveball into this one. It's not a biggie, but it's something that you have to worry about. You may notice it, you may not, but you will if you do the problem the right way, which is to write down the given information first. So copy that down, and let's write down the given information to the side. And you're going to notice something about this. One of the first things you got to realize when you write down the given information is you're not doing it just for easy problems like this. You're going to have to do it for harder problems. All right, so it's going to get complicated. There's going to be times when you have 6, 7 variables, and you want to keep them straight in your head. But today it's pretty easy. We have C, wavelength, and frequency, right? Everybody agree with that? Those are the three things. What's my C in this problem? Yeah, C is the speed of light. It never changes. It's written on the board over there. 2.998 times 10 to the 8th meters per second. You do not need to memorize that. I'm going to give it to you on the test. Wavelength. What's my wavelength in this problem? 5.59 times 10 to the negative 5th centimeters. Everybody agree with that? Everybody see where that comes from, right? Okay. And finally, frequency. What's my frequency in this problem? It's my unknown. It says find the frequency. Okay. So we're all set. But remember, there's another reason we're writing this stuff down to the side. So we can check our units. Not only are we picking stuff out of a complicated question, which this isn't that complicated, but we're also making changes if there are unit problems. And there are. I've got meters and centimeters in the same calculation. Can't have that. I've got to change one guy to the other. And I suggest changing the centimeters to meters. So I put centimeters at the bottom, meters at the top. 1 meter contains 100 centimeters. Now, let's use a little. You can, if you had to. Just plug that into your calculator and divide it by 100. You shouldn't have to. You should be able to use your head. Am I going to make that number bigger or smaller by 2 zeros? Smaller. Everybody agree? Because it's in the bottom. I'm dividing. How do I make a -5 smaller by 2 places? Make him what? Negative what? No. -7 is smaller than -3. We had that problem last time, remember? 5.59 times 10 to the -7th meters. Now he's in. Now they're in the same units. I've done the first step. I told you before, the first step is often the hardest. Picking the guys out of the equation, making your unit changes, that's often the hardest part. The next part is getting a little harder this time. Last chapter, we only had one equation, D equals M over V, that you could possibly choose from. This time, we have 2 equations I could choose from. It could have been this one, or it could be this one. Right? How do you know which of the 2 equations I'm using in this problem? What do you think, Emily?
It's like frequency.
Yeah, since it has frequency and wavelength in this problem, I look for an equation that has frequency and wavelength. And it's this one, right? So that's why I know I'm using this guy. So I write down the equation C equals wavelength times frequency. However, he's not set up properly. How do I set him up correctly? What do I have to solve for in this case? F, right? So what will I do to both sides? I'm looking for F. Got to get him by himself. What will I do to both sides? No, I will not divide by F. And I keep getting that. This should not be happening in this class. You guys all had algebra in probably 8th grade. I'm going to divide by wavelength, and that will leave F by himself. So F would equal C over wavelength. And let's plug our numbers in. This is the last step and the easiest step by far. 2.998 times 10 to the 8th meters per second over the wavelength, which is 5.59. I'm sorry, yeah, over there, 5.59 times 10 to the -7 meters. Okay, get your calculator out, plug that in, what do you get? What did you get here? Jared, what'd you get?
5.36.
Times 10 to the what?
14.
10 to the 14th. You all agree with that? Okay, that's the right number of significant figures. That's the right exponent. What are my units?
Seconds.
No. And I know everyone's going to say seconds, but it's not. Let me show you something. Everybody watch this. You're going to say seconds because meters cancel and leaves you with seconds. But where are those seconds? Where are those seconds? They're on the bottom, right? This is meters per second, correct? So you actually get 1.36 times 10 to the 14th, some kind of thing called 1 over seconds. What the heck is that? You can write that down. We're going to change it in a second, but we can write that down. What the heck is that? Think back to the kid on the stick. Okay? Think back to the kid on the stick. Let me make a wave. Kid was standing here on a stick, right? And the waves are going by. And as their waves are going by, he's counting. 1, 2, 3, 4. And then when they go by faster, 1, 2, 3, 4, 5, 6, 7. Okay? And he's counting how many waves go by per minute or per second. Okay? That's where this comes from. The 5.36 times 10 to the 14 waves went by per second. We have a special name for that, for frequency. Something that means per second. You know what it is? It is hertz. Not the rental car, but the same hertz that's on your radio stations. What's your favorite radio station? 97.9. What is the number for it? 97. What's the name of it? 97.9. What's the actual, like, KRZ, whatever. What is 97.9?
Yeah, it's good.
It's not KRZ. KRZ is 98.5. It's KRZ.
No, it's just
Okay. Oh, okay. It doesn't have an actual name to the station? Okay. Well, either way, you have Magic 93, 97.9, 98.5. All of those are, you know what they mean? That's how many megahertz. That's the wave. That's the wave frequency that station's broadcasting in. So that when I tune my radio station to that frequency, I get their broadcast. Okay? So that's what hertz means. Now, of course, the ones in your radio dial are in megahertz. Okay? There's an M before it. But you look at your station when you're driving home today on your radio dial, if you have one, and it will say, as you're tuning, next to it somewhere, MHZ usually. Okay? Hertz. Hertz means how many waves go by per second. Okay? It's kind of weird, but that's what it means. How many waves are going by per second? Your units come out to be 1 over a second.